Okay, we just went over the exam solution. The next thing on your to-do list for this class anyway is homework 11, which is having to do with hydraulic jumps. If I remember correctly, there's just 3 problems on that assignment. Has anybody looked at that so far? So hydraulic jump problems are relatively easy. They're pretty fun. So that assignment before class on Friday, and then just as the reminder that the final project report is due on Monday the 18th of April. So we're going to go into the lab for just a minute and look at 2 different things we can do to change the location of a hydraulic jump. So let me pause the recording. Let's pack up just briefly. We'll be back. Okay, so we were just in the lab looking at the hydraulic jump, and I wanted to explain there's a plastic piece at the end of the flume that I dropped into place, and the purpose of that was to force the depth in the flume towards the far left side, to force the depth higher. And we could still have a hydraulic jump without that plate in place, but it wouldn't be quite as visible as otherwise. Like, remember we looked at these different jump types in class on Monday, and we might be able to, just by adjusting the slope of the flume and adjusting the height of the gate, we might be able to induce an undular jump or a weak jump, but the ratio of the upstream and the downstream depths is pretty close together, and so it's just not as much to look at as if you're able to force it into a stable jump by putting this plastic plate downstream. So this is just to force the depth to be relatively high, and then when you have a high depth here, then that allows the more dramatic ratio of the depth, stronger looking rollers that are easier to spot. So one of the empirical formulas that our book provides, there's a couple of different techniques that our book provides, is how long the jump is going to be. And what we were looking at, I guess I should have thought to point it out at the time, is in a hydraulic jump there is a section of relatively rapid disturbed water that are called the rollers, and they're annotated here on this figure that's in our book with an R. And then there's a more subtle and gradual increase in depth beyond the rollers, the overall length of the jump. Our book has this nomograph. It's a figure that's produced by the Bureau of Reclamation just to show you how long the jump would be. The overall distance from the initiation of turbulence, where this rapid flow variation begins, up to and including the rollers, but then some section beyond the rollers where the flow is still increasing in depth until it reaches the normal depth and stays at the normal depth downstream. So the way that you use this nomograph is that if you know the Froude number of the upstream section, so calling location 1 is just the depth immediately prior to the jump, if you know the Froude number there, then you can go up and from this nomograph, you'd bounce off of this nomograph, and then to the left read the ratio of the length of the jump to the downstream depth. So for instance, if you had a Froude number of 4 prior to the jump, so we go up with this white line, intersect the black one, and then to the left, that's about 5.75. So 5.75 is equal to the jump length to the downstream depth y2. So then if you knew the downstream depth y2 from using the Bellinger momentum equation, which is this one, Bellinger momentum equation, if you'd calculated y2, then you can calculate the length of the jump. So the jump length would be whatever factor you look up off of the nomograph, which varies as a function of the Froude number, multiplied by the y2 downstream depth. And so it's just their way of allowing people to approximate how long the jump will be. And the reason why it matters is that, remember, the hydraulic jump is dissipating a lot of energy, and there can be quite a bit of turbulence, and so you may need to have some sort of special armoring and reinforcement and making sure that whatever's at the bottom of the channel in the section where a hydraulic jump is expected to prevent any sort of damage to the channel. So you want to know how long the jump is going to be just so that you can protect and reinforce that section. So our book presents this nomograph as one technique. They also offered another suggestion that the length of the rollers fraction of that is usually 40 to 70% of the overall length. And so when the Froude number is relatively low, then the roller length is 40%. But then when the Froude number is very high, when the Froude number is 9, then it's about 70% of the overall jump length would be those visible rollers. And then you could numerically interpolate in between. There's something called the Hager jump equation, which makes use of the hyperbolic tangent function to calculate the length of a hydraulic jump. And so again, it's dependent on the Froude number and knowing, in this case, the upstream depth. So that's just another way that they've tried to use empirical observations to predict how long the hydraulic jump might be. And then our book doesn't give a name to the third method they describe. It just calls it another jump length equation. And they have a coefficient that varies between 5 to 6.9 multiplied by the difference of the upstream and downstream depths. So just to get some practice with how to use the nomograph, the hyperbolic function, and the other jump length formula, let's take a look at this case where the water is flowing at a velocity of 5 meters per second. We know that the channel is 25 centimeters wide, and then the depth of flow upstream of the hydraulic jump, so that's Y1, is 10 centimeters. So we'll find, first of all, the jump depth downstream of the jump. So we'll use the Bellinger momentum equation for that to find the depth downstream. And then we will approximate what the jump length might be by a couple of these different methods. All right, so the first thing we have to do is calculate the Froude number, because that's going to be both in the jump length equation, but it's also in the equation for finding the downstream depth, Y2. So we have a flow rate of 0.125 cubic meters per second that we get from having the depth Y1 is 0.10 meters. The velocity is 5 meters per second. And then the width of the channel is 25 centimeters, and so B is 0.25 meters. Okay, so the area is B times Y1. That gives us an area of 0.025 square meters. And then Q is V times A. So it's the 5 meters per second multiplied by 0.025 meters squared. Okay, so I already kind of gave away that we've got this flow rate, 0.125 cubic meters per second. And we can put that into the Froude number equation here. So the Froude number is the square root of Q squared times the top width of the channel. Here it says T. That's just the variable definition that's used in some other texts. For our purposes, we've been using capital B to mean the top width of a channel this semester. Divided by G times A cubed. And then all of that's to the 1/2 power. Okay, so the flow rate, 0.125 cubic meters per second, squared times the top width of 0.25 meters, divided by G, which is 9.81 meters per second squared, times the area, 0.025 0.25 meters squared, and we need to cube the area, and then this entire quantity we take to the 1/2 power. Okay, so let me just show you on screen these calculations so far. Okay, so our Froude number is 5.05. 5.05, and if we go to the classification of different hydraulic jump types, this is in the range of a stable jump. This is the one that's most advantageous simply because the flow velocity isn't pointed towards the bottom of the channel, and it stays in place. It's not meant to drift back and forth in terms of its location. Okay, so we've got a 5.05 for the Froude number. So now if we look at this figure, Froude number of 5, so here's in between the 4 and the 5, we go up and find the point of intersection with that figure and then take it to the left. So it's slightly above 6. What I had written in my notes previously is I think that the LJ to Y is going to be 6.1 when we get to that point. We need to know, oh, that's to the Y2. So we don't yet know the downstream depth after the hydraulic jump. So the downstream depth after the hydraulic jump, Y2, is Y1 divided by 2. So the Y1 depth that we were given, the upstream is 0.10 meters times -1 plus the square root of 1 plus 8 times the Froude number squared. The Froude number that we're putting in there is 5.05, and we'll square that. Okay, so when we do, the depth after the jump is 0.666 meters. Okay, so now if we substitute that into this ratio that comes from the nomograph, you can see that that estimates the length of the jump will be 4.06 meters because it's saying the jump length is 6.1 times the downstream depth. And if the downstream depth is 0.666 meters, we multiply that by 6.1, it's predicting 4.06 meters. All right. Now, the next method uses the hyperbolic tangent function. Do you have that in your calculator? Tan H? Yeah?
You gotta click the hyper button.
Click the hyper button?
Yeah, it's like
All right.
HYP button.
HYP. And then tan?
And then it gives you the option of all of them and then the inverses.
All right. So let's take a look at what are the substitutions we need to do into this formula. So the first method suggested that the length of the jump may be 4.06 meters. Okay, so this next technique says that the jump length, L sub j, is y1, so 0.10 meters, multiplied by 220 times tan h times 5.05 divided by 22. Okay, so 5.05 divided by 22, that is 0.2295. So I want to do tan h of 0.2295. I've got it on my calculator. Let's see. Okay, so tan h of 0.2295 is itself 0.2256. So according to the second method, it suggests that the length of the jump will be 4.96 meters. So it's still in the same ballpark, roughly. These are just all empirical approximations of how long that jump might be. And then the other one, the book doesn't really give us much indication whether to use, remember there's a coefficient in front of it. The coefficient varies between 5 and 6.9. I just said, well, what would it be if we used 5.5? Maybe I should have used more in the middle. Maybe 6 is more in the middle. But, if the A value is 5.5, then that would give us a jump length of 3.113 meters. Now, it's basically these two methods that I have the most confidence in, the nomograph method by the Bureau of Reclamation and this hyperbolic tangent function. So it's suggesting that the jump length is going to be between 4 and 5 meters. Whereas this other approach said 3.1. Okay. Now let's, in the time remaining, talk about gates. The simplest kind of a gate is just a piece of metal that's set into a frame. You can see this has a piece of rebar that's been welded to the top, and using this gate, the purpose of it is to regulate flow, not to quantify flow. Most of the hydraulic structures we've talked about before now, like flumes and sharp-crested weirs and broad-crested weirs, the purpose of those structures has been to quantify the flow rate rather than to change the flow. But an underflow gate like this would be used, let's say, in a drainage ditch to control how much water goes into a field from a canal. And it can be as simple as just a plate in a frame, or it can be far more sophisticated than that. You can see here's a cast iron gate that has a hand crank, or they can put a motor at the top, because these can get relatively heavy if they have to reinforce them for the pretty high pressures that can occur when submerged at a certain depth. They may have gates in irrigation networks. They'll have gates sometimes at water treatment plants and wastewater treatment plants to allow water to flow in and out of settling basins and flow equalization basins. There are radial gate designs that are intended to avoid the pressure of water pressing on a flat surface like this. And if you have a relatively deep channel and the water's pushing this frame up against pushing the plate against the frame, then you'd not only be lifting up the weight of the metal, but you're also trying to overcome the effects of friction holding that gate into place. And so these radial gates have the advantage of overcoming that frictional effect, and I'll show you a side view of one in a minute that basically just sends the forces through a central pin and reduces any friction effects, and you're just dealing with the weight of the gate in a case like that. Looking at it from the side, what we can use to analyze the different depths is the specific energy analysis. And so the amount of energy that there is in the water upstream of the gate, we can calculate based on the depth and the velocity head, and use that to predict how much the velocity is going to be after the gate when we are able to measure a given depth. So here, if we know the Y2, which here we're saying is partly related to how wide open the gate is. So if you know the height that the gate is open to, there's going to be some contraction that continues to occur even after the water exits the underflow gate, because there's pressure behind it. So the water continues to speed up a little bit, and the depth is decreasing, and it'll finally come to some stable depth that is the coefficient of fraction multiplied by the gate height of the opening. Since most gates are rectangular in shape, then we could do this on the basis of flow per unit width, lowercase q. And so here, the flow per unit width can be a function of the upstream and the downstream depths. And this can be useful for problem solving. A typical coefficient of contraction is 59 to 62% as the water continues to accelerate after coming out from underneath the gate. All of this, of course, assumes that there's no energy loss. And just for these initial steps of calculating depths, we'll go with that, although there are energy losses, and the coefficient of discharge that we use to calculate the flow capacity through a gate will reflect the energy losses. So this is that side view that's showing some gates will be radial, and the forces that are acting on this curved surface point towards the axis of rotation, which avoids the friction of the plate pressing up against the frame that it's in. But in both cases, whether it's a frame or a radial gate, the water flows along the bottom of the channel, which is great for avoiding the sediment issues we've talked about before with broad-crested weirs and sharp-crested weirs, where as the water slows down approaching a gate, sediment that was previously entrained and kept moving because of the water's velocity, as the water velocity slows down, then particles begin to settle. And so it's good that we've got this underflow gate, because then it can draw them through the opening of the gate and prevent it from getting clogged. This orifice equation with the coefficient of discharge does account for the energy losses as the water goes through it. And here, B is the width of the channel, W is how open the gate is, and then we use the square root of 2gy1 to give us the velocity. You may remember that when we talked about the orifice equation in fluid mechanics, we said V equals the square root of 2gh. Now here, we're just saying the upstream depth is the height of the water, and so we're using this term to give us the velocity, multiplying it by the width, and now we've got velocity times width gives us, the width and the height is an area together. So velocity times area gives you flow rate, and then the coefficient of discharge takes into account the energy losses that arise in part because of the contraction. You can calculate the coefficient of discharge here by the ratio of the upstream and the downstream depths. And since we're out of time, we're not going to be able to go through this example. We'll pick up on Friday with this first gate example. We'll do both of the gate examples on Friday. But for today, just know that those hydraulic jump problems are due before class on Friday.